The SI unit of work is joule, while the CGS unit is erg. So what is 1 joule? 1 joule is 1 Newton meter, which means the force of 1 Newton to move the body by a distance of 1 meter. While 1 erg is basically 1 dyne of force to move a body by 1 centimeter. So the relation between joule and erg is 1 joule is equal to 10 raised to 7 erg. This is an important relation which you need to remember. Now, after covering our work, let's move to the next concept of power. So the rate at which the work is done is called power. So how do we understand what power is? As we say, it is the rate at which work is done. So we have P is equal to W by T, which means work done per unit time. But work done is equal to F into S, and here we have T. But S by T is basically displacement upon time, which is the velocity. So P is equal to F into V, which means that it is the force into the velocity or the speed. So power in terms of instantaneous values, P is equal to dE by dt. And the unit of power is watt, which is basically joule per second, and the CGS unit is erg per second. Now let's move to the next concept of energy. Energy is basically the ability to do work. So it is analogous to work. So all the relations which are applied to work are applied to energy as well. This happens because when we try to do some work on a body, the kinetic energy of the body increases. So as work is done, kinetic energy increases. And similarly, when an opposing force is applied on a body, the Ke decreases, the kinetic energy decreases. This decrease in kinetic energy is equal to the work done opposing the force. So as opposing work is done, a negative kinetic energy comes into force. So as the work done is positive, we have a positive kinetic energy. As the work done is negative, we have a negative kinetic energy. It's not negative, work cannot be negative. So as the work decreases, we have a negative kinetic energy. So my kinetic energy Ke is equal to half mv squared, where m is the mass of the object, while v is the velocity at which it is moving. Velocity or the speed of the body. While my potential energy, which is the energy when the body is at rest, is given by mgh, where m is again the mass of the body, g is the acceleration due to gravity, the value of acceleration due to gravity is minus 9.8 meters per second square, while h is the height at which the body is placed. So the relation between kinetic energy and momentum. Now we know momentum is P, which can be given by mv. So the relation between kinetic energy and momentum is, so we have Ke is equal to half mv squared, that is equal to half mv into v, which is half P times v. Or else K is equal to P squared, so that's half mv square upon 2m. So these are my relations for kinetic energy in terms of momentum. Now, as I said, work and energy are analogous. So let us see the work energy theorem as which shows how work is related to energy. So the work energy theorem states that the work done on the body or by the body is equal to the change in the net kinetic energy. So work energy theorem so let's say we have a body which is at rest on a surface, and we want to move this body through a small distance PQ. Let's say it has moved by a small distance ds after a force F is applied on the body. So we know that the small work done dW is equal to F times ds, but we also know that F is equal to mass into acceleration. So dW is equal to ma times ds, but my acceleration is equal to change in velocity per unit time into ds. So I get, let's swap these two terms. So I get ds by dt times dv. Now what we see is, let us, this basically is equal to v, mv dv, which is basically my dw. Now the total work to increase the velocity from u, so u is my initial velocity, it may be at rest or I am increasing my force, so u would be a value, while v is my final velocity. So as I increase my velocity from u to v, let us see what is the relation between the work and the energy. So let us find work, which is basically the integral from u to v dw, which is m integral u to v times v dv. Now the integral of this would basically be v square by 2 under the limits of u and v. So we get m times v square by 2 minus u square by 2. This means that I get the equation for w is equal to half m times v square minus u square, half m v square minus half m u square. This is my final kinetic energy, while this is my initial kinetic energy. So my work energy theorem says that the work done is basically to change my final kinetic energy minus my initial kinetic energy. So it's basically the change in the kinetic energy. This is my work energy principle. The law of conservation of energy states that energy cannot be created nor destroyed. It can only be converted from one form to the other. And the total energy of the universe is the same, which means that my total kinetic energy plus the total potential energy, which basically means that this is my total mechanical energy, is equal to constant. So what exactly happens is my potential energy may increase while the kinetic energy decreases, or my kinetic energy increases and the potential energy decreases, but the total energy remains constant. So from now on, let's define a new concept called coefficient of restitution. Of restitution. Which is given by E. So this coefficient of restitution is basically the ratio of the magnitude of impulse during the period of restitution to that during the period of deformation, which actually means that it is the relative velocity after a collision. So v2 minus v1 upon the relative velocity before a collision, so u1 minus u2. So say for example we have two bodies, this body 1 and body 2. Body 1 was moving with an initial velocity u1, and this body 2 was moving with an initial velocity u2. After collision, it moved with a velocity of v2, and this will, sorry, v1, while this will move with a velocity v2. So we say that the coefficient of restitution is basically the relative velocity after the collision to the relative velocity before the collision. So let's see these three cases. What will happen when body 1 collides with body 2, and after the collision both the bodies move with the same velocity, which basically means that E is equal to 1. Therefore, V2 minus V1 will be equal to U2 minus U1 minus U2, sorry, U1 minus U2. This condition is known as a perfectly elastic collision. So basically when my two bodies move with the same velocity after collision, the relative velocities of the two bodies before and after collision are the same. This condition is known as a perfectly elastic collision, and therefore E is equal to 1. Let's say E is lesser than 1. In this case, V2 minus V1 will be lesser than U1 minus U2. This case is known as an inelastic collision. So the value of E basically depends upon the extent of loss of kinetic energy during the collision. Now, what if E is equal to 0? If E is equal to 0, we say that V2 minus V1 is equal to 0, or V2 is equal to V1, which means that both the bodies will move at the same velocity after collision. So in case 1, we saw the bodies will move, but the initial velocity and the relative velocity before collision and after collision will remain equal. However, in the third case, we see that v2, that is the velocity after collision for both the bodies, is the same. This condition is known as a perfectly inelastic collision. So we have the relative velocity is equal. In that case, E is equal to 1. So that condition is called perfectly elastic. If E is lesser than 1, it's called an inelastic collision, which means that the relative velocities before collision will be greater than the velocities after the collision. While if V2 is equal to V1, which basically means that E is equal to 0, we get a perfectly elastic collision. In an elastic collision, both momentum and kinetic energy are conserved. So the momentum and kinetic energy are conserved, and this is this is an important concept. So in case of an elastic collision in one dimension, say for example you're taking a one dimension collision of an elastic collision. So basically we have two bodies. U1 is the initial velocity, V1 is the final velocity, and in this case U2 is the initial velocity and V2 is the final velocity. So we have the relation V1 is equal to m1, where m1 is my weight, mass of my first body, while m2 is the mass of my second body. So m1 minus m2 upon m1 plus m2 into u1 plus 2m2 times upon m1 plus m2 times u2. This is my equation for my final velocity of my body 1 after an elastic collision. How do we get this? We get this basically by equating my law of law of conservation of momentum and then the law of conservation of kinetic energy. Sorry, of basically of energy. Conservation of energy. So we equate these two laws. We equate the first law, we get an equation. Then in terms of second one, we get another equation. And then we substitute values of v2 in terms of both in order to get a relation between v1, u1, u2, and the mass of the body. So we are eliminating the value of v2. Another relation of v2 is basically m2 minus m1. Notice the change in the values of the masses upon m1 plus m2. That remains the same. Here there will be a switch u2 plus, here we take 2 m1 times upon m1 plus m2. So the denominator always remains the same, it's just the numerator is changing. And here again we have u1. So this is my velocity, final velocity of my first body. This is my final velocity of my second body. These are the velocity values after an elastic collision takes place in one dimension. These values are very important when you're solving numericals in one dimension.